వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతుంది. 2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning. Yes, up to now we discussed about the Fourier series, two forms, trigonometric form as well as exponential form, right? In Fourier series form we discussed about the how to find out the coefficients by using the formula a0, an and bn. After that these three coefficients will be written in the periodic function m of t. After that it will be converted into polar form, that is s of t. M of t can be replaced by s of t for our more convenient form. It is more convenient form. For our convenience it will be converted as s of t equal to s naught plus sigma n equal to 1 to infinity sn cos n omega naught t minus phi n. After that we will write mod Sn, that is square root of an square plus bn square, and phi n equal to minus tan inverse bn by an. Okay, after that we will draw the amplitude and phase spectrums, right? Similarly, in the same manner, coming to the exponential Fourier series form, here also we will find out the signal can be decomposed as a combination of, here the arbitrary signal m of t can be decomposed as a combination of two signals. Okay, here cosine signal and sine signal. So here also we will find out the two coefficients, Fourier coefficients c0 and cn. So cn equal to sigma n equal to 1 by t naught sigma n equal to c. In the earlier class we already saw some problems also. Okay, see sigma, see here, c naught equal to 1 by t naught integral t naught to t naught plus t naught m of t dt, and cn equal to 1 by t naught integral t naught m of t into e power minus jn omega naught t dt for n is not equal to 0. So based on these formulas, so we'll find out some problems also. We have done some problems also. So after knowing the c0 and cn, we will know the mod cn, that is magnitude spectrum, and phase spectrum, that is theta n. Okay, by knowing the mod cn and theta n values, we will draw the amplitude spectrum and phase spectrum. Okay, so next we are going to discuss about the Dirichlet conditions. What are Dirichlet conditions? This is a very important one. This may ask for 2 marks questions also. Okay, so what are Dirichlet conditions? We have three Dirichlet conditions are there. First condition is over any period, whether it is 0 to infinity or minus infinity to infinity, over any period x of t must be absolutely integrable. So x of t must be absolutely integrable over any period. That is represented as integral t mod x of t dt must be less than infinity. Okay, it is some finite value, it is not infinite value, it is some finite value. That's why it is represented as integral t mod x of t dt must be less than infinity. So over any period, so that is the first Dirichlet condition. Over any period x of t must be absolutely integrable. Next, second one is x of t have a finite number of maximas and minimas with any finite interval. During the finite interval we have minimum number of, that is a finite number of maximas and minimas, not infinite number of maximas and minimas. Only we have finite number of maximas and minimas during the finite interval. That is the second Dirichlet condition. And the third one is x of t have a finite number of discontinuities within any finite interval. Okay, x of t have a finite number of discontinuities. Here the discontinuities also we have the finite number of discontinuities within any finite interval. All must be finite only, not infinite. Furthermore, each of these discontinuities must be finite. Here the discontinuities also must be finite. So here everything will be finite. This that should not be infinite. So first one is x of t must be integrable, absolutely integrable, and which should be less than infinity. That is represented by integral t mod x of t dt is less than infinity. And second one is x of t have a finite number of maxima and minima within any finite interval. And third one is x of t have a finite number of discontinuities within any finite interval. These discontinuities must be finite also. Okay, so these three are the Dirichlet conditions, very important. Next we will see the relation between trigonometric and exponential Fourier series. Okay, already we know the trigonometric Fourier series and exponential Fourier series. What is trigonometric Fourier series? M of t is equal to a naught plus sigma n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. Yes, that is a trigonometric form of Fourier series. And coming to the exponential form of Fourier series is given as m of t is equal to sigma n equal to minus infinity to infinity cn into e power plus jn omega naught t. Okay, so e power j theta is nothing but e power j theta is cos theta plus j sin theta. Okay, so here we are taking e power plus or minus j and omega naught t. So substituting for e power plus or minus j and omega naught t in terms of sinusoids in the sense harmonics. Whether these are sinusoidal, these are in the form of sinusoidal form or cosine form. Okay, so we can write this as cn into uh, e power plus or minus j and omega naught t. So that will become m of t equals c naught plus c1 into, here if n is 1, then c1 into e power plus or minus j omega naught t can be written as a cos omega naught t plus j sin omega naught t, plus c2 into cos 2 omega naught t plus j sin 2 omega naught t, plus c3 into cos omega naught t plus j sin 3 omega naught t. Similarly, in the negative side, c minus 1 into cos omega naught t minus j sin omega naught t, plus c minus 2 into c suffix minus 2. This is cos 2 omega naught t minus j sin 2 omega naught t. Here we are writing this exponential form in terms of its sinusoids or harmonics. So that is nothing but e power plus or minus e power plus or minus j theta is equal to cos theta plus j sin theta. Okay. Similarly, e power minus j theta is equal to cos theta minus j sin theta. In the same manner, we will write e power plus or minus j n omega naught t. That is cos n omega naught t plus or minus j sin n omega naught t. Right? Okay. It is equal to c naught plus here we are taking common as a cos omega naught t. Cos, if we take cos omega naught t as common, then c1 plus c minus 1 into cos omega naught t. Similarly, j sin omega naught t is taken as common, that is c1 minus c minus 1. In the same manner, c2 terms and jc2 terms. Okay, so this will become c naught plus c1 plus c minus 1 into cos omega naught t plus c2 plus c minus 2 into cos 2 omega naught t up to cn plus c minus n into cos n omega naught t plus j c1 minus c minus 1 into sin n omega naught t plus j c2 minus c minus 2 into sin 2 omega naught t plus dash 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 plus j cn minus c minus n into sin n omega naught t. Okay, let it be taken as equation number 1. Next, coming to the trigonometric form of Fourier series, that is m of t equal to a naught plus sigma n equal to 1 to infinity a n cos n omega naught t plus b n sin n omega naught t. Let it be taken as equation number 2. Okay. Next, by comparing equations 1 and 2, we will get here a naught equal to c naught. Cos n omega naught terms are these are the cos n omega naught terms, and these are the sin n omega naught terms. So an equal to cn plus c minus n, and bn equal to j into cn minus c minus n. Okay. Okay, so the above can be rearranged. This expression can be rearranged to get C naught, Cn, and C minus n terms, C minus n in terms of the quotients of the trigonometric series a naught, an, and bn. Here we are writing these are the quotients of the exponential Fourier series. These are the coefficients of the exponential Fourier series. These can be written in terms of trigonometric Fourier series. And here, these are the exponential Fourier series terms can be written in terms of trigonometric Fourier series. Okay, quotients of the trigonometric Fourier series. Okay, by adding these two, we will get these expressions. Okay, we will explain. I will explain once again this relation between trigonometric and exponential Fourier series. So let us take initially the equation of the exponential form of Fourier series, that is m of t equal to sigma n equal to minus infinity to infinity cn into e power jn omega naught t. Let us take e power jn omega naught t as plus or minus e power plus or minus jn omega naught t. This is in the form of e power plus or minus j theta. So e power plus or minus j theta can be written as cos theta plus or minus j sin theta. Okay, so it is in the same manner we will write this e power plus or minus j n omega naught t as a cos n omega naught t plus or minus j sin n omega naught t. Okay, so simply we will expand this one. So m of t equal to c naught plus c1 into cos omega naught t plus j sin omega naught t plus c2 into cos 2 omega naught t plus j sin 2 omega naught t plus dash 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 plus c minus 1 into cos omega naught t minus j sin omega naught t plus c minus 2 into cos 2 omega naught t minus j sin 2 omega naught t. Okay, so here we are taking real terms on one side and imaginary terms on another side. So c naught plus c1 plus c minus 1 into cos omega naught t. Similarly, j sin omega naught t into c1 minus c minus 1. In the same manner, c2 plus c minus 2 into cos 2 omega naught t plus j sin 2 omega naught t into c2 minus c minus 2. Now you will write the only real terms on one. Initially, we will write the real terms first. After that, we will write imaginary terms. Okay, then c naught plus c1 plus c minus 1 into cos omega naught t plus c2 plus c minus 2 into cos 2 omega naught t plus dash 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 plus cn plus c minus n into cos n omega naught t plus j into c1 minus c minus 1 into sin n omega naught t plus j into c2 minus c minus 2 into sin 2 omega naught t plus dash 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 plus j cn minus c minus n into sin n omega naught t. Okay, so this is taken as equation number 1. Now refer the trigonometric form of the Fourier series, that is m of t equal to a naught plus sigma n equal to 1 to infinity an cos n omega naught t plus bn sin n omega. Now compare these two equations. So c naught becomes a naught. An is equal to cn plus c minus n. Bn equal to j into cn minus c minus n. By rearranging these equations, we will get the expressions for c naught, cn, and c minus n in terms of an, a naught, and bn. Similarly, here we are getting the expressions for cn and c minus 1 in terms of c minus n and c naught in terms of a naught, an, and bn. So this is the relationship between the trigonometric form of Fourier series and exponential form of Fourier series. Is it clear? Yes, we'll go for the next chapter. Next, representation of a periodic function by the Fourier series over the entire interval. Entire interval means from minus infinity to plus infinity. So representation of a periodic function. Periodic function, how the periodic function is represented? It satisfies the condition m of t is equal to m of t plus capital T for all values of t. Okay, that is periodic function. So that periodic function uh, should be represented over the entire interval. Entire interval means from minus infinity to plus infinity. From minus infinity to plus infinity. Okay, right. So, we discussed about so far we discussed about the periodic function over the interval t naught to t naught plus t naught. T naught to t naught plus t naught means it is some finite interval. It is some 0 to t, 0 to 5, or 0 to 10, like that. It is some finite interval. Outside this interval, now we are seeing the outside this interval, Fourier series need not be equal. It need not be equal. It may be differ, right? So up to some finite interval it may be equal. Fourier series may be equal, but beyond that beyond that it need not be equal. So Fourier series, first of all we will see the Fourier series representation over an interval. This is limited interval, this is finite interval. T naught to T naught plus T is f of t is equal to sigma n equal to minus n infinity to infinity fn into e power plus jn omega naught t during this interval T naught to T naught plus T. That is taken as equation number 1, where omega naught, that is angular frequency omega naught equal to 2 pi f naught, that is 2 pi by t. The two sides of the equation 1 need not be equal outside this interval. So up to some finite interval, as we already discussed, up to some finite interval, that is from t naught to t naught plus t, Fourier series may be equal, but beyond that interval it need not be equal. Okay, it need not be equal. That's why we are considering the RHS side of the equation number 1, that is f of t, and this is this one, sigma n equal to minus infinity to infinity fn into e power j n omega naught t can be considered as phi of t. So phi of t is equal to, here we are representing f of t equal to phi of t, where phi of t is sigma n equal to minus infinity to infinity fn into e power j n omega naught t for all values of t. Let us take this equation as equation number 2. Here what we have discussed here is during the finite interval Fourier series may be equal, but beyond that interval it may not be equal. Okay, that's why we are doing this analysis. That is here the right hand side during the interval t naught to t naught plus t may be considered as phi of t. So f of t equal to phi of t, where phi of t is sigma n equal to minus infinity to infinity fn into e power jn omega naught t for all values of t. Let us consider this as equation number 2. Right. It is simple to show that the function phi of t is a periodic function with period t. So we can show this phi of t as a periodic function. Any function x of t, suppose if you take x of t, if you want to show the x of t as a periodic function, then it has to satisfy the condition x of t is equal to x of t plus capital T for all values of t. Here also phi of t is a simple periodic function. We can show this as a periodic function. If it is a periodic function, then the right side of the equation number 1 is also a periodic function, right? So that's why we are showing this phi of t as a periodic function. So consider the function phi of t plus t. What is the condition for showing phi of t as a periodic function? It has to satisfy the condition phi of t is equal to phi of t plus t, right? That's why first of all we will calculate phi of t plus t. We will analyze phi of t plus t. So equation 2 becomes phi of t plus t is equal to replace t by t plus t. So sigma n equal to minus infinity to infinity fn into e power j n omega naught t into t plus capital T. Okay, e power x plus y, that is nothing but e power x into e power y, right? So we can write this as equation that is sigma n equal to minus infinity to infinity fn into e power j n omega naught t into t plus capital T is nothing but 2 pi by omega naught. Why? Because here we have written omega naught equal to 2 pi by t, or omega naught into t equal to 2 pi, or t equal to 2 pi by omega naught. So replace t by 2 pi by omega naught, right? Right. Okay, now we will expand this e power ax plus bx, that is e power ax into e power bx. It is in the form of e power x into e power y. Okay, sigma n equal minus infinity infinity fn into e power jn omega naught into t into e power jn omega naught into 2 pi by omega. So omega naught gets cancelled, so e power j 2 pi n, right? So it is equal to sigma n is minus infinity to infinity fn into e power j n omega naught t into e power j 2 pi n. Since n assumes only integral values, that is 0 plus or minus 1, 0 plus or minus 2, plus or minus 3, etc., it is obvious that e power j 2 pi n is equal to unity. Suppose if n is 0, if if n is 0, e power 0, that is 1. Okay, and hence this phi of t plus t is equal to sigma n equal to minus infinity to infinity fn into e power jn omega naught t. That is nothing but phi of t. Here phi of t are equal to phi of t plus t. So it satisfies the condition phi of t is a periodic function or periodic signal. Okay, phi of t is a periodic signal. So now we can say that the periodic function by the Fourier series over the entire interval. So over the entire interval also it is a periodic. The function is a periodic. Okay. So f of t is a periodic over the entire interval. So beyond the finite interval also it is a periodic. Okay. So first of all, during the finite interval, Fourier series may not be equal. Beyond that, it must be equal. During the finite interval, it must be equal. Beyond that finite interval, it may not be equal. So, when it will be equal, if that function should be shown as a periodic. If it is a periodic, then we can say that it must be a periodic series. Fourier series must be a equal, must be equal during the beyond that interval also, beyond that finite interval also. Okay, so during the finite interval it is represented as f of t equal to sigma n equal to minus infinity to infinity fn into e power j n omega naught during the finite interval t naught to t naught plus t, right? So where omega naught is 2 pi by t or t equal to 2 pi by omega naught. So the two sides of the equation need not be equal outside this interval. So the right hand side should be considered as phi of t. It is equated to phi of t. First of all, we have to show that phi of t must be periodic. What is the condition for showing the periodic for any signal? So that should satisfy the condition phi of t is equal to phi of t plus t. So first of all, we will analyze phi of t plus t. So phi of t plus t is this one. So expand this one. So you'll get sigma n equal to minus infinity to infinity fn into e power j n omega naught t e power j 2 pi n. So it is integral values. N is the integral values, so that it will become e power 0, so that its value is 1. Okay. So then it will phi of t plus t is equal to sigma n equal to minus infinity to infinity fn into e power j n omega naught t into 1. That is phi of t. So phi of t is equal to phi of t plus t. So both are equal. Then it is nothing but the periodic function by a Fourier series over the entire interval. So beyond the finite interval also it is equal. Okay, Fourier series is equal. Already we shown, right? Next we will see the examples of a periodic function. Periodic function. Examples of periodic function. See, this is the periodic function. Periodic function. What is meant by periodic function? With some particular time period, it will be repeated up to infinity. Then wherever it starts with some finite duration or finite time period, it will be repeated. See here the time period is 1 second shown in this figure. Time period is 1 second. With this time period f of t having a 1 second time period, it will be repeated. Okay, so this we can say that this is a this is a periodic signal. Representation of f of t and its Fourier series over the entire interval minus infinity to infinity is as shown as so Fourier series. Its Fourier series is represented like this. So this is the given periodic signal. Its Fourier series is represented like this. Okay, with amplitude capital A. So it is nothing but f of t equal to e power minus t like that. Okay, so this is a periodic function f of t with period t can be represented by a Fourier series exponential or trigonometric form over the entire interval minus infinity to infinity, that is f of t equal to f of t plus t. It has to satisfy the condition f of t equal to f of t plus t. But f of t in exponential form can be represented as sigma n equal to minus infinity to infinity f of n into e power plus j n omega naught t during the interval minus infinity to infinity. Consider this as equation number 5. where omega naught equal to 2 pi by t, and Fn, this is the Fourier quotient, that is 1 by t integral t naught to t naught plus t f of t into e power minus jn omega naught t dt. This is equation number 6. This is simple example for our understanding purpose. They have given like this. So here they have taken the periodic function first. After that, we will take the Fourier series of this periodic function. So Fourier series can be expressed in terms of f of t as like this. Here Fn is a Fourier quotient that is represented like equation number 6. Okay. So this is about the representation of a periodic signal over the entire interval. Representation of a periodic function by the Fourier series over the entire interval. Here what we have shown is beyond the limited or finite interval, we can show that we have shown the Fourier series must be equal. Actually, beyond the finite interval, it need not be equal. But here we shown the Fourier series is equal beyond the finite interval. Okay, is it clear? Next, we will go for the properties of Fourier series. Properties. What are the properties of Fourier series? This is very important. It may ask for 7 marks also. Okay. So the very important properties of Fourier series are linearity. First one is linearity property. Next one is time shifting. Next, frequency shifting, time scaling, time differentiation, convolution, multiplication, and symmetry property. We have 8 properties. Those are linearity property, time shifting property, frequency shifting property, time scaling property, time differentiation property, convolution property, multiplication property, and and symmetry property and symmetry property. Okay, what is linearity property? So linearity property, how it is defined? So it is defined like this. See the last expression, z of t equal to a into x of t plus b into y of t tends to czn, that is equal to a into cxn plus b into cyn. Okay, a into cxn plus b into cyn. So see, let us take the complex exponential Fourier series is expressed as x of t equal to sigma n equal to minus infinity to infinity cn into e power jn omega naught t. Here x of t is any continuous time period signal and cn is Fourier quotient, as we already know these parameters. For simplicity, let us denote these quotients as cxn. So cn can be denoted as cxn for our convenience. So x of t, its Fourier quotient is Cxn. X of t Fourier quotient is Cxn. Then the linearity property may be stated as if the Fourier quotient of x of t is Cxn and Fourier quotient of y of t is Cyn, then z of t equal to is a combination of a into x of t plus b into y of t. The Fourier quotient of this entire expression as Czn is equal to a into Cxn plus b into Cyn. Is it clear? Simply we can say that a into x of t plus b into y of t, z of t, that entire thing is equated to z of t. The Fourier quotient of z of t is Czn is equal to a into Cxn plus b into Cyn. Let us take the Fourier quotient, Fourier series, exponential Fourier series expression, that is x of t equals sigma n equal to minus infinity infinity cn into e power jn omega naught t. Here x of t is the continuous time periodic signal ct sign. ct ct here ct represents continuous time Fourier series. Okay, so see, x of t is continuous time periodic signal and cn is Fourier quotient of x of t, right? For our simplicity, we will consider the cn is cxn. Since it is x of t, the periodic signal is x of t, then it is cxn. If it is z of t, czn. If it is y of t, cyn. Okay, right. So the linearity property may be stated as if the continuous time Fourier series of x of t is a cxn and continuous time Fourier series of y of t is cyn, then z of t is stated as a into x of t plus b into y of t. The continuous time Fourier series of entire expression is equal to czn is equal to a into cxn plus b into cyn. This is a linearity property. And second one is time shifting property. How it is stated: if the continuous time Fourier series of x of t is cxn, then time shifting property. Here the time will be t will be shifted towards right side or left side by t naught units. So x of t minus t naught, the continuous time Fourier series of x of t minus t naught is e power minus j n omega naught t naught into c xn. So the magnitude of Fourier series quotients remain unchanged when a periodic signal is shifted in time. Here the magnitude is what is magnitude is Cxn is the magnitude or coefficient, right? Okay, if x of t, the continuous time Fourier series of x of t is Cxn, then the continuous time Fourier series of x of t minus t naught is e power minus jn omega naught t naught into Cxn. Okay, next property is frequency shifting property. Here the frequency is shifted. Okay, right. Here the continuous time Fourier series of x of t is cxn. Then the continuous time Fourier series of e power jn into omega naught t into x of t is cx into n minus n naught. Okay, cx into n minus n naught. This is cxn, but here cx into n minus n naught. Here shifting the frequency components. Here time will not be shifted, but frequency will be shifted. Shifting the frequency components by n naught is equivalent to the terms of x of t and e power jn omega naught t. So this is a frequency shifting property, right? So first one is linearity property. Next, time shifting property. Time will be shifted, and the third property is frequency will be shifted. So time will be shifted in the sense x of t minus t naught becomes e power minus jn omega naught t naught into cxn, and whereas in the frequency shifting property e power j n omega naught t into x of t can be shifted as a cx of n minus n naught. Okay. Next property is a time scaling property. Here the time scaling, it will be time will be scaled or compressed x of at or x of t by 2 like that. Okay. It states that if x of t is a periodic signal with a period t, then x of t will be a periodic signal with a period b by alpha, where alpha is the positive real number. Positive real number. Thus, the application of the time scaling property, the period of a signal changes. Okay, so time scaling property applies to each of the harmonic components of a signal x of t. Therefore, Fourier quotient for each of these harmonics components remain the same. So simply mathematically it is simple. It is explained as if the continuous time Fourier series of x of t is cxn, then continuous time Fourier series of x of at is 1 by a into cxn. Okay, so thus after time scaling, Fourier series quotients are same. The spacing between the frequency components changes from 1 by t naught to a by t naught. Okay, so x of at is also cxn. That is called time scaling. So the waveform will not be changed. It can be compressed or expanded. In time scaling, the waveform will be expanded or compressed only. Next one is time differentiation property. Time differentiation. If the continuous time Fourier series of x of t is cxn, then differentiation d by dx of x of t. The continuous time Fourier series of d by dx of x of t is j into 2 pi n by t naught into cn. Okay, so this is the differentiation property. D by dx of x of t, the continuous time Fourier series of d by dx of x of t is j into 2 pi n by t naught into cn. Next, time convolution property. Time convolution property is defined as if continuous time Fourier series of x of t is cxn, then continuous time Fourier series of y of t is cyn, then z of t equal to convolution x of t convolved with y of t, the continuous time Fourier series of x of t convolved with y of t is equal to czn equal to t naught into cxn into cyn. So the convolution in time domain will become simple multiplication in frequency domain. Next, multiplication property. So it is stated as if a continuous time Fourier series of x of t is cxn and continuous time Fourier series of y of t is cyn, then the multiplication will become convolution in frequency domain. So z of t is equal to x of t multiplied by y of t. The continuous time Fourier series of x of t multiplied by y of t becomes cz equal to some constant t naught into cxn convolved with cyn. So see the difference here. See the convolution in time domain becomes simple multiplication in frequency domain. Similarly, the multiplication in the frequency time domain becomes simple convolution in time domain. Next, last property is a symmetry property. It is defined as if x of t is real, then cn star becomes c minus n, and if x of t is imaginary, then cn star becomes minus of c minus n. What is minus of c minus n? It is reversal of this one. Okay, minus of c minus n. So this is a symmetry property. Cn star becomes, if it is real, cn star becomes c minus n. If it is an imaginary, then cn star becomes minus c minus n. Okay, these are the important properties of our Fourier series. Very very important. These are all very important. There is a compulsory question on this one. It may be asked for 7 marks also. Okay, this is please concentrate on this one. So these 8 properties are very very important. With this we will conclude this today's session, and the next class will continue the remaining topics. Thank you.